Welcome to Geometry, Measurement, and Probability. During this semester, we'll be looking at probability, we'll look at statistics, and we'll look at many topics in geometry. We have a great semester ahead of us, so let's get started with Chapter 9 and talking about probability. In Section 9.1, we'll start looking at what is probability and how do we calculate it. We'll look at both experimental and empirical probabilities. We'll talk about properties of probabilities, and we'll look at what we call mutually exclusive and non-mutually exclusive events. First, we have an experiment. An experiment is an activity whose results we can observe and record. Now, every possible result of our experiment is called an outcome. And when we list all the possible outcomes, that gives us our sample space. Within a sample space, we can have a specific event. And so an event is a subset of a sample space. We can represent our sample space in three different ways. First, we have a drawing. That's figure A. In figure B, we have a tree diagram. And in figure C, we have a set. Now, if you've taken real number system, you should remember that a set is listed with the funny braces. If you haven't taken real number system, now you know. Sets are listed with the wavy braces around them. So let's look at example 1. Suppose we have an experiment in which we're tossing a fair die. Now, die is one, dice is plural. In part A, we are asked to find the sample space. First, we're going to draw the sample space. So I draw each of the sides of the die. We have 1, 2, 3, 4, 5, and 6. Then I'm going to represent my sample space with a tree diagram. Now, because a die has 6 sides, I'm going to draw lines coming out of the same point. The numbers on the die are 1, 2, 3, 4, 5, 6, and so I list each of those with one of those possible lines. Then when I list my sample space as a set, our sample space is listed with a capital S, and I list my numbers with commas in between them. Notice again that a set is listed with the wavy braces around it. In part B, we are looking at event A, which is rolling a 5. Now, the outcomes in an event make up a set, and so as we list those outcomes, we will also list them in the wavy braces. So we list A equals, and notice I put the 5 in the wavy braces. Part C, we're looking at event B, which is rolling an even number. So I'm going to list the even numbers that I find on a die. I have B equals 2, 4, 6, and notice again that I've listed these in the wavy braces. That is the correct mathematical notation. Event C is rolling a prime number. So the prime numbers on my die are 2, 3, and 5. Notice I wrote C equals, and I put 2, 3, and 5 in the wavy braces. Now, our experimental or empirical probability is another way of saying that. It's what's going to happen in the long run. We look at what actually happens in the real world with experimental or empirical probability. We have what we call relative frequency. This is the ratio of the number of times a certain event happens to the total number of times we repeat our experiment. In other words, we write in the numerator of our fraction how many times our event occurred, and in the denominator of our fraction, we write the total number of times we repeated the experiment. The relative frequency is our experimental or our empirical probability. Empirical probability is based on observation, and so it cannot be calculated directly. And one other note as we look at our probabilities can be stated as fractions, and make sure you simplify those fractions as decimals or percents. Use your directions carefully, because Math Labs will tell you in what form you need to write your answer. So let's suppose we toss a coin 100 times, and the coin lands on head 64 times. So our experimental probability would be 64 over 100. Now always simplify your fractions. 4 goes into 64 16 times, and 4 goes into 125 times. And so our experimental probability here is 16 over 25. If we roll a die 100 times and the die lands on 14 of those, then our experimental probability of obtaining a 6 is 14 out of 100 because the die landed on 14 times. And simplify your fraction. 2 goes into 14 7 times, and 2 goes into 150 times, and so our experimental probability is 7 over 50. Now, let's move and talk about theoretical probability. First, the way that we write probability is with a capital P. If we're looking for a specific event, we'll write that event in parentheses, and you'll notice that events are represented with capital letters like P, parentheses, and E. Or if we're looking for just an outcome, we'll still write that outcome in parentheses. And outcomes will be denoted with lowercase letters. And so we'd have P and then the lowercase letter in parentheses. We use our theoretical probability when all of the outcomes of an event are equally likely. And so we can directly calculate our theoretical probabilities. Now, the more times we repeat an experiment, the closer that experimental probability gets to theoretical probability. For instance, you know that the probability of tossing a head on a coin is 1 out of 2 because there's one head out of 2 sides. Now, that doesn't mean that when I toss a coin, I'm going to get exactly half heads and half tails. Say maybe I toss the coin 100 times. I might get close to half heads and half tails, but not necessarily exactly. But the more times I toss that coin, the closer I'll get to half heads and half tails. This is what Bernoulli's theorem, or the law of large numbers, says. The more times we repeat an experiment, the closer our experimental or empirical probability gets to that theoretical probability. The way that we calculate our probability, say we're looking at the probability of event A, we look at how many elements are in A divided by how many elements are in S, and remember S denotes our sample space. So, in example 2, our sample space is the whole numbers 1 through 25. We are going to select a number at random. So that means that all of our numbers have the same chance of being drawn. And we're going to find some probabilities. Event A is the probability that an even number is drawn. First, I want to list all of the even numbers in my sample space. Then second, I'm going to find my probability. My notation is a capital P and a capital A in parentheses. Notice that we have 12 even numbers listed in event A. So we have 12 divided by, there are a total of 25 numbers, and so our probability is 12 over 25. Event B is that a number is greater than 25. Well, if we look back at our sample space was the whole numbers 1 through 25. There are no numbers greater than 25 in our sample space. Our notation for the probability of B is a capital P with B in parentheses. There were no numbers greater than 25 divided by 25 total numbers, and 0 over 25 is 0. This is what we call an impossible event. An event that's impossible, that can't happen, notice it has a probability of 0. Now look at part C. Event C is that a number less than 26 is drawn. Our notation is a capital P with the C in parentheses. All of my numbers are less than 26, so I have 25 numbers less than 26 divided by 25 total numbers, and 25 over 25 is 1. This is what we call a certain event, and a certain event will have a probability of 1. In part D, we want the probability that a prime number is drawn. Again, the first thing that I'm going to do is list all of our prime numbers. Now remember, a prime number is a number who has no factors other than 1 in itself. So from the whole numbers from 1 to 25, our prime numbers would be 2, 3, 5, 7, 11, 13, 17, 19, and 23. And now I'll find my probability. Our notation is a capital P and the D in parentheses. Notice that there are 9 prime numbers listed, so I have a 9 in the numerator, divided by 25 total numbers, gives me a probability of 9 over 25. And last we have part E, the event that a number that is both even and prime is drawn. So as I look at that list of prime numbers, 2 is the only number that is both even and prime. My second step is to find my probability. Make sure you use the correct notation, a capital P with a capital E in parentheses. There is one number that is both even and prime, divided by 25 total numbers, gives us a probability of 1 over 25. In part B, we talked about an impossible event has a probability of 0. And in part C, we had a certain event, which has a probability of 1. Our probability will always be between 0 and 1, and that's what Theorem 9.2 says. Join me in the next video as we pick up with mutually exclusive events.